When an AI agent executes a long horizon task, reading documents and pursuing complex reasoning steps, it inevitably hits its physical limit. The active context window fills up, exhausts the token allowance, and the model crashes. The standard industry fix for this is heuristic compaction. An external script monitors the context window, and when it reaches a fixed threshold, like 90%, a subroutine automatically triggers, summarizes the oldest messages, and deletes the original text. But an external script has no understanding of the agent's actual reasoning process. It cuts blindly based on token count, summarizing and permanently deleting raw context, precisely when the agent might be in the middle of a delicate logical deduction. The Agentic Context Management Framework, or ACM, proposes a different mechanical approach. Context compression must be an intentional action. It should be initiated by the model's own reasoning, exactly when the model decides it is appropriate, rather than being forced by a passive, invisible threshold. Stripping away the hard threshold forces the architecture to treat memory management as a first-class tool use problem. The agent takes control of its own operating constraints, aligning its internal autonomy directly with the external limits of the hardware. This chart tracks token count over time to map out what an agent-directed memory system actually looks like. It creates a sawtooth context profile. The working memory grows as the agent gathers data, drops sharply when the agent initiates a compression action, and then immediately begins growing again. For this system to function reliably, that compression step must be structurally lossless. The working view that the model sees shrinks, but the raw data it discards is never permanently destroyed. Achieving a lossless state requires a strict archive before delete code sequence. When the model decides to compress, the system first copies the raw data slice to the disk, saving it as a discrete JSON file. Only after that archive file is secured does the system delete those tokens from the active window. Because the raw data lives on the disk, the agent can use specific recall tools later in the run to fetch those exact files back into its working memory. If the architecture reverses this sequence, or fails to save the raw files entirely, the agent cannot trust its own compression tools. It will inevitably hallucinate missing details when trying to resolve long horizon dependencies. To make this level of agency possible, the ACM runtime orchestration strips away unnecessary complexity. It runs a bare React loop, exactly one LLM call per turn, followed by a flat switch statement for tool dispatch. But the model cannot time its compression actions if it cannot see its limits. So, before every single turn, the harness calculates a conservative mathematical projection of how many tokens the next step will consume. As we see in this React loop flowchart, that projection is injected directly onto the model's final tool observation message. It is formatted as a literal text string, acting as a highly visible turn-by-turn field gauge. From there, the loop operates autonomously until it hits one of 5 specific termination paths. It finds the final answer, exhausts the max iterations, hits a hard context window error, or triggers one of 2 failsafe prompts. Notably, if the model's reply is simply truncated for length, the loop does not terminate. It injects a retry prompt, instructing the model to generate a shorter tool call, and the loop continues. The 2 failsafe paths, a forced stop and a forced compress, only activate if the model mismanages its budget and hits 95% of the total context window. They are architectural backstops, not the intended method of operation. By replacing opaque external scripts with a highly accurate text budget, the architecture gives the model the specific data it needs to exercise total agency over its operating constraints. When the model reads its token budget and decides it is time to compress, it calls a tool called manage_context. This tool takes 0 arguments. The model initiates the action, but the system determines the exact range of messages to compress. That range is routed to a dedicated summarizer LLM. This secondary model plans its compression inside a distinct think block and then outputs a strict memory body, adhering to a strict rule against conversational preamble. This animation illustrates the critical compress_range execution. The system takes a deep copy of the raw message slice, bundles it with the new summary, and writes it directly to the local disk. Deletion from the live working memory executes only after the disk archive is confirmed and locked. This rigid mechanical ordering enforces the lossless invariant. To utilize that archived data, the model uses a counterpart tool called query memory. To call it, the agent must pass the specific identification number of the summary file along with a targeted query. Instead of dumping a massive summary back into the context window, query memory runs an LLM extractor over the archived raw messages on the disk, pulling out and returning only the specific fact the model requested. Isolating the live working view from the archived raw data prevents context bloat, while preserving the granular historical facts required to solve long-horizon dependencies. The active runtime surface for all of this consists of just 4 highly restricted tools: search, get document, manage context, and query memory. Their JSON descriptions are long and behavioral, doubling as explicit in-context strategy for the model. This 3-column diagram maps the file-backed memory architecture. The working memory is the live message list the model sees. The episodic raw is an append-only mirror that survives all compression, and the archival tier holds the discrete JSON files queried by the recall tools. Noticeably absent is a semantic or vector tier for agent memory. While face is installed as a dependency, it is utilized entirely for initial document retrieval, not for recalling agent history. Because the archival summaries are strictly immutable, the architecture carries a zombie memory risk. Stale text from old deductive dead ends can inadvertently resurface when the model queries the disk. Rather than implementing a highly complex cache eviction policy, the system mitigates this risk by feeding the model refetch hints, pushing it to verify data against the raw documents, and flagging degraded summaries for offline review. From a security perspective, the runtime lacks a permission layer entirely. There are no approval gates and no capability scoping. While this is typically a severe vulnerability, the risks of excessive agency are contained by the tool design itself. The action surface is completely retrieval only. With zero code execution and no ability to mutate external state, a complex permission gate is architecturally unnecessary. Supplying the model with budget data and compression tools is only half the engineering challenge. A baseline 9 billion parameter model lacks the innate reasoning required to successfully time its own context compression. To bridge this capability gap, the runtime inference loop we just analyzed doubles as the rollout generator for a 6-stage post-training orchestrator. Looking at this conveyor mapping the 6 stages, we zoom in on stage 2. Here, GPT-5 acts as a teacher, evaluating the student model's failed trajectories. It analyzes the context limits and surgically picks the exact turn where managed context should have fired. In stage 3, this synthetic, corrected turn is spliced directly into the initial history. The student model then resumes the rollout from that specific point to generate a successful path. Moving down the pipeline to stage 4, a massive 397 billion parameter teacher model analyzes these generated trajectories to score top K log props. Because running a 397 billion parameter VLM alongside the training loop exceeds standard GPU constraints, these log props are cached offline to a static .npz file. This hard split makes the pipeline strictly off policy. The 9 billion parameter student model trains solely off the cached file, and after just one gradient step, the student's behavior begins drifting from the dataset it is training on. To counteract this drift and maximize the teacher signal, the architecture applies a strict pass-it-for filter. It deliberately discards the easy wins, retaining only the hardest, most complex trajectories for the student to learn from. Off-policy distillation is a direct compromise for hardware limits, but by utilizing the primary inference loop to generate tightly controlled, heavily filtered failure states, engineers can distill highly precise timing intuition down into smaller deployable models. Relying on arbitrary external thresholds to manage context bloat guarantees failure in long-horizon tasks. The ACM repository provides 3 distinct takeaways, shown on this summary slate. First, context compression must be engineered as a direct model action, fueled by an uncompromising budget signal. Second, the lossless invariant is non-negotiable. Raw data must be written to disk before it is deleted from live memory, ensuring factual recall is always possible. And third, a minimalist React loop can serve dual purposes, acting as both the runtime execution harness and the exact data generator needed for offline distillation. True agent autonomy requires equipping a model to responsibly offload, manage, and query its own internal history.